Hi, my name is Ricky, and the robot that I will explain in the video is called the balancing robot. The robot balances itself by measuring the tilted angle that it's currently in and then makes the tilted angle decrease to 0, which is the desired angle. If the robot reaches the desired angle, the robot then balances. First, how do you find the current angle that the robot is in? To find the angle tilted that the robot is in, it uses two sensors. First, the robot uses an accelerometer. The accelerometer uses arctangent to find the angle. Specifically, if the acceleration magnitude of the x, y, z vector is added up, it equals to the value of gravity, which is 9.81. Therefore, the square root of x squared plus y squared plus z squared equals to 9.81. The image shows the tilted accelerometer. If the sensor is tilted from the image above, the angle of x-axis can be found by using trigonometry. This is the equation that shows the angle value of the x-axis. The sensor finds the magnitude of acceleration of x, y, z vector. Then the values are inputted in the equation, which gives the tilted angle of the robot. Secondly, the robot uses gyrosensor. Gyrosensor measures speed from each x, y, z axis and uses integration of the sensor to find the distance of the angle. Accelerometer and the gyrosensor finds the angle rho, pitch, yaw of the robot. Rho represents the angle that the robot is tilted in the x-axis. Pitch represents the angle that the robot is in the y-axis. Yaw represents the angle that the robot is tilted in the z-axis. However, the angle for the y-axis is unnecessary, since the two wheels already balance the robot, so that the angle for the y-axis is always 0. Therefore, angle for the rho and yaw will only be considered. Although the accelerometer produces accurate angle value when robot stays still, it produces errors when the robot is moving, because the turbulence of the robot and the sound produced by the motor changes the value of the angle instantaneously. On the other hand, gyrosensor is insusceptible to the little turbulences and the sound produced by the motor, since it solely uses angular velocity to find the angle. However, the error of the angle gets larger as time passes due to integral errors. In here, the blue graph represents the angle value obtained from the accelerometer, and the red graph represents the angle value obtained from the gyroscope. The blue graph shows the constant oscillation of the angle value as the time passes. This happens due to the sound produced by the motor. The red graph shows that as time passes, it keeps getting upward. This happens due to integral error. Therefore, to reduce the errors produced by both sensors, I use complementary filter. Complementary filter is simply combining the angle value obtained by the accelerometer and the gyrosensor. This equation shows the complementary filter equation. In this equation, y equals to the modified angle, n equals to time, x gyro equals to the angle derived from the gyrosensor, and x acceleration equals to angle derived from the accelerator. Gain is a constant value ranging from 0 to 1. As the gain value goes closer to 1, the value of the gyrosensor is much more influential than the value of the accelerator. As the gain value goes closer to 0, vice versa. Therefore, I manipulated the gain value so that the error obtained from the noise of the motor and the time delay created by the gyrosensor is minimized. From using the angle value obtained from the complementary filter, we can control the motor's output to make the robot to reach the steady angle. To do this, I used PID variable. P represents proportion, I represents integration, and D represents derivation. P simply makes the angle of the motor to decrease to the desired angle by making the motor go the same direction that the robot is falling. Although P helps to decrease the angle error in the short term, the robot will ultimately not gain balance, which means that the robot will keep moving or keep shaking. This happens because P does not make the motor go slower or faster while it's approaching, since its only goal is to make the robot reach to the balancing angle. The error obtained from this is called steady state error. I helps to reduce the steady state error by adding up all the errors from the past. D makes the motor of the robot slower or faster as it reaches towards the desired angle to make the motor stop at the desired angle. Therefore, D improves the steady state error, reducing the robot from shaking too much as it reaches towards the balancing angle. In easier terms, it predicts the future. However, the noise of the motor sometimes gives huge error to the D term because the noise of the motor might change the angle value even the angle value is at a steady rate. And the D term will try to make the motor slower or faster to bring the angle to zero, although the angle itself is at zero, making the robot lose its balance. Let's look at the example of how the robot reacts when these values are added. First, only P variable is implemented. When the force is applied to the robot either continues to move to the direction of the force, or it shakes and loses its balance, because it takes a lot of time for the P variable to settle down and gain balance. Although the robot seems to have gained balance, it will continue to move in a straight direction because of something called steady state error. Steady state error is an error that the P variable solely cannot solve. Next, P variable and I variable is implemented. P makes the steady state error and I helps to decrease the steady state error. Because of the property of the robot, the steady state error still remains, although the I decreases the steady state error. Therefore, the robot still shakes or keeps moving forward, but this time a lot smaller than last time. Lastly, P, I, D variable is all implemented. With the D term added, the robot would quickly come to stop and gain its balance even more quickly than the PI, because the D term helps the robot to make the robot slow down as the robot is approaching the desired angle. Thank you for watching.